Good morning, Astronomy 1020. Welcome to Lecture 2, Part 2, and Homework 2. Today we are going to practice a little more of the coordinates that we learned on Tuesday, and we're also going to sort of drift on to discuss things like planetary orbits and Kepler's laws. Hey, Paige, I'm just noticing you got a cute pooch there, and you know I take an interest in these things. Tell me all about this guy. Who is that?
That's Lily.
Yeah, Lily's cute. We want to see more of her.
She just jumped up on my bed.
Well, that's okay. I mean, you know what they say about letting sleeping dogs lie, but when Lily's around, we want to see her. We want to see her face. We like the animals. I can't believe the cat. Oh, look at that guy, huh? All right, we're ready to learn some astronomy today. Therapy dogs and therapy cats. We need them. Okay. She seems pretty mellow, actually. Let's get to it. Yesterday, I'm sorry, not yesterday, but on Tuesday, you guys learned how to use two coordinate systems to describe stars in your local sky. You learned about the horizon system, and you learned about the equatorial system. Let's talk about the horizon system for a second. Let's say, I'm taking a peek at the stars outside at night. Say I, take a walk over to slide number 50, and I look up at a star in my sky. What sort of angles would I use to describe this? What do I want to use? How about a stamp? Boop. Why is it yellow? Anyways, how would I describe that star?
So the point overhead of you would be the zenith, or Z.
Okay, I'm with you. That's your zenith.
Yeah, the zenith, and then you have
your altitude, which will be like the red arrow that will be.
No, this is your altitude. The altitude is your degrees above the nearest horizon.
All right, thanks. Just
And keep going. If that's Lionel or whoever, just keep going. What else?
you also have your meridian, which is an arc that rises due north, reaches through the zenith, and sets due south.
Okay, the meridian is an important guiding line or an important reference mark. But in the horizon system, the meridian is not one of our angles or coordinates that we use. The meridian is a line.
Yeah.
But in a way, Caitlin, I was asking for things like altitude, like how do I describe the position of that star?
Okay. Yeah, then you have altitude and then azimuth, which is degrees along the horizon clockwise from the north.
Right, so in other words, north is here.
Yeah.
And my star is in the northwestern sky, so I'd have to go clockwise all the way around to that coordinate location. I could also substitute direction. I could call that star northwest. I could say, oh, it looks like it's up about 50 degrees above the horizon in a direction northwest. So northwest is kind of a valid azimuth. But if I were going to do a technical azimuth, I would say, let's see, 270, plus 45. Why is my brain not working this morning? Who can do that faster than me? 315. I should have known that. 315 would be the azimuth. Okay, cool. Let's practice this. Ooh. Oh no, students, I've got the focus issue again. The focus issue. What am I going to do? Okay, because I changed all of my settings because of that internet troubles I was having. Let's see, Logitech. Okay, I figured out how to do this the day after our first lecture. What I need to do is I need to open up my ridiculous Logitech program. I need to deactivate my camera. So let's put on the crappy little camera underneath, okay? And then Logitech can take control of my camera for a minute. Supposedly, yeah?
Yeah.
Supposedly I can go to Zoom through this, but I haven't really figured that out. I'm not smart enough to figure that out just yet. All right, so autofocus. That's what it keeps doing. It keeps going to extreme focus. That's autofocus off. And now I can take off the camera. And now I go back here, and this should fix it. Let's see if it works. All right. That's why they pay me the big bucks. Okay. Now,
Professor,
yeah.
before you go on, after the diagram you just showed, can you just show me what the difference between zenith and altitude was again?
Sure. Let's take a peek. The zenith is a particular point on the sky, right? And the zenith is this point right here. It's the point directly over the head of the observer. Now, this presumes that you're the observer dude. Let me get my drawing tool again. And the observer is standing here in the middle of the field. So there's your stick man, okay? So you're an observer in the middle of this grassy field. The zenith is a point over your head. That does not change. That is fixed. But the altitude depends upon what doodad you're looking at. If I'm looking at a star right here, its altitude are the degrees above my nearest horizon, like so. If I'm looking at a star in my southern sky, its altitude is the degrees above the nearest horizon over there. So I can have a million different objects on my sky that I'm looking at, but the zenith is a fixed point.
Good.
That help?
Yep.
Cool. Another good way to enforce these ideas is to practice with a little game. Let's try to make a two-dimensional view of our local sky. And let's make it the Rhode Island's local sky, as we are, in some way, Rhode Islanders, or at least we're here now, I think. Take out that ruler that I've advised you several times to get. Leave a lot of headroom, go halfway down your page, and I would recommend a 10-centimeter line. Mark the midpoint at 5 centimeters, and then from the midpoint, make a dot 5 centimeters above where the top of the dome should be. 5 centimeters is the radius of your circle, that is your sky. So we can make, as I've done before, a few points to help guide our dome drawings. I'm going to make 3 or 4. Cut quick. All right, and then connect the dots. Draw on the dome of your local sky. Well, mine could have been a wee better, but. Okay, this is a two-dimensional drawing. So let's put north on the right. Let's put south on the left. Even though it's 2D, I'm going to kind of shade in some ground here. I'll put an observer dude at the center of the field. And I will draw in the observer zenith, now that we know what that is. Let's mark it with a Z. As we've talked about before, in the Rhode Island local sky, you are in the northern hemisphere, so you should be able to see the North Celestial Pole, and that's roughly where Polaris is. So let's make a line about halfway up the page or so, not exactly, but close to it. Let's label that NCP for North Celestial Pole, and I'll even put Polaris there on the sky. The celestial equator is actually running east to west in this diagram. And I've got a north to south cross section. So I can't really draw the celestial equator because it comes in and out of the plane of the board. But what I can draw is I can draw a line that goes from my observer up to where the celestial equator intersects my meridian. And for 2D, that's probably about as good as it gets. I'm going to be careful to make this as close to a 90-degree angle as I can. I think that's right. I'll make a dashed line here and label that CE for Celestial Equator. Next, I'm going to label, you'll notice that we have 1, 2, 3, 4 angles in this diagram. And I'm going to label those angles alpha, beta, gamma, and delta. Those are the first 4 letters of the Greek alphabet. Let me see if I can get some better contrast here. It's customary in physics and astronomy to use Greek letters for angles in honor of the Greeks who loved and developed geometry. Okay, let's try a test of your knowledge of the horizon system and of the equatorial and of the geographical system. Now, this is going to be a wee bit abstract, but one of these angles, represents your latitude on Earth. It's a direct representation of your latitude on Earth based on the definition of latitude. Someone want to give that a shot? Hey, I want to say something else here while I'm at it. I've been asked to hold some live Zoom lectures, which I'm happy to do. I also have perfectly good recordings of these things. Now, a lot of people say, you know, geez, Brendan, I really like the live experience. I didn't sign up for this sort of distance learning stuff, which is fair. But you guys also have a certain obligation to share some video with me and to interact with me. And so far, a good number of you are, but I know how this game works. As the semester goes on, fewer and fewer people are going to do that. There will come a point where I'm just going to be like, hey, just watch the pre-recorded lectures. Don't make me give the same lecture again to just a bunch of black squares, right? And sometimes people prefer it that way, which is fine too. But I don't think it's fair to have it both ways, where you want the live experience but don't want to participate. That's the mind mess that I don't understand. So why doesn't someone out there in the non-troll audience read me the definition of latitude from your notes last time?
Latitude is the degrees north or south of the equator.
Okay, so let's imagine drawing in the Earth as a sphere, the way we're used to thinking about it. And let's try to put the observer in the same orientation. I'll make North Pole of Earth here, and I'll make the equator, I don't know, here. And I'll even use the same colors to help, okay? So I'll use blue for the North Pole and South Pole. So there's my North Pole for Earth, right? And the equator is perpendicular to that line. Let's put the observer so that their head is up, just like kind of in our diagram. Okay, so there we are in Rhode Island. We're about halfway up. And if you think about this, full screen here. This is a line from the center of the Earth to the foot of the observer. Now, how did you define the latitude again?
It's degrees north or south of the equator.
So if this is the equator and this is you, then your degrees north of the equator is this angle here. That is your latitude, right?
Mm-hmm.
Okay. So how does this relate to the angles that we have on our local sky?
Well, if it's a 45-degree angle, if it's
No,
a
I did not say it was a 45-degree angle. I kind of made it halfway, but we don't want to presume that you know what that angle is yet. It's just an abstract angle, but I'm trying to figure out which letter represents it.
Would it be beta?
Pardon?
Would it be beta?
Yes, absolutely. You can see that now. Because the angle between the equator and your feet is your latitude. But that should also be the same angle between the zenith and the celestial equator. The equator points towards the celestial equator, your feet point towards your head and the zenith, right? So beta is your latitude. Okay, so actually let's write that down. So if we asked which angle represents your latitude, the answer would be beta. Yeah, latitude. Suppose I asked you about the altitude of Polaris. Can you tell me which angle would represent the altitude of Polaris?
Would it
Oh,
be gamma?
Not gamma.
I think it'll be Y.
Sorry?
No, I don't know. The one that's next to the B, the one to the, I don't know how to say it. I don't know if it's a Y.
Alpha looks like a
No, no.
Jesus fish. Beta looks like a squiggly B. Gamma looks like a squiggly Y. Delta looks like a squiggly D.
Oh, I was gonna say gamma, but never mind.
What's the definition of altitude?
Degrees north or south of the equator.
Nope.
No, it's
Latitude.
degrees of a star above the nearest horizon.
Degrees above the horizon. Degrees above the nearest horizon. Where's the horizon in this diagram?
It's technically at the ground where our feet are, which is north.
That's not good enough. Sorry, Caitlin, that's not good enough for me. The horizon and the ground are not exactly the same thing. Because the line that I drew is the ground. It's this, right? That's the line that I drew. But that line is not the horizon. Where is the horizon in this diagram?
Oh, it's the 360-degree base.
Right, this is the horizon. In fact, the horizon only intersects my diagram at 2 points. Where are those 2 points?
North and south.
Yeah, so this is your northern horizon right here. Maybe we should make note of that. And this is your southern horizon. So if the altitude of Polaris are degrees above the nearest horizon, then the angle that represents the altitude of Polaris should be what?
45 degrees.
Once again, I don't know. We're not assuming, first of all, this is a variable for a reason, Caitlin. It could be any old angle. And we could be anywhere from here to there. And we're not presuming which one. I drew it kind of halfway up to represent an arbitrary latitude. In fact, I'm actually regretting that. I wish, Caitlin, now that I'm hearing you say that over and over again, I wish instead I had drawn the picture to be like this, so it was more extreme. Maybe I need to do that next time to make it more arbitrary. Mikey says it's delta, and that's correct. The angle between the northern horizon and Polaris is the altitude of Polaris, because the northern horizon is the closest horizon point to the North Star. So that's the, damn it, I keep writing latitude. This is the altitude of Polaris. Okay, now we can put in specific numbers. If this is for the Rhode Island's local sky, Caitlin, then our latitude is not 45 degrees. Our latitude is what angle?
I'm sorry, what was the question again? Our altitude was what angle?
What's the latitude of Rhode Island?
The latitude of, I only have Providence and Charleston, so.
That sounds good to me.
Okay, so between like 41 and 42
Degrees.
degrees north.
Thank you. So this angle here is 42 degrees. Because that's our latitude. Now I spy with my little eye a 90-degree angle between the north celestial pole and the celestial equator. If beta is 42 degrees, what should gamma be?
Is it 48 degrees?
That's right, because 90 minus 42.
It wasn't fast enough.
Say that?
No, never.
You guys having fun over there, Lionel?
No, 'cause I was like, fuck, I wasn't fast enough.
Hey, I see another right angle. I see another 90-degree angle between the zenith and the horizon.
That would be 42, correct?
Say that again, Caitlin.
That would be 42 degrees, correct?
What's that? What's
Delta would be 42 degrees.
excellent. And while you're at it, what would alpha be?
That alpha would be 48 degrees.
Cool. Now, although we did this for a Rhode Island local sky, with these angles here being our latitude and these being 90 minus our latitude, these two relationships should hold wherever you go on Earth, because it'll always be 90 degrees from equator to North Pole, and it will always be 90 degrees from horizon to zenith. So if you change your latitude, these angles stay the same and those angles stay the same. They're just 90 minus each other. So in a way, we've proved a very useful and fundamental result. And the result sounds something like this. The altitude of Polaris is equal to your latitude. And that is a fundamental and useful result that is not obvious before you do this problem. So box it, put some stars next to it. I'd even surround it with beams of fire so that you never forget this important mantra. It will help you solve problems in astronomy, especially like during an exam. Very important diagram that we just made here. You can make this diagram too when you're working on a problem or when you're working on a test question. You can quickly make it, especially if you have a little protractor or something, and you can solve some tricksy problems. Let's test out our skills. May I erase? Okay. Here's our homework today is actually pretty epic. So I'm trying to train you right now for it. Let's try a question that's going to come up during our homework today. In-class question. Describe the location of Polaris in the Rhode Island local sky. How would I do that?
So, before we go to that, you said that altitude equals your of Polaris equals your latitude. How come that doesn't change like during the day, like the Earth is spinning? Don't you see Polaris
Great question.
differently?
Every other star in the nighttime sky does change. But because Earth is spinning on an axis which points towards the north celestial pole, over the course of a nighttime or even a 24-hour day period, come on, the stars are all rising in the east and spinning in the west, and they're all orbiting around Polaris. I think I mentioned before that you can find Polaris in your sky by using the two stars of the Big Dipper, which we call the pointer stars, and they make a line pointing towards Polaris. If you take a camera and point it towards Polaris and leave the shutter open during the course of the night, stars will seem to rotate in orbit around Polaris. Okay, so Polaris is not exactly at the north celestial pole. It's doing a tiny, tiny little orbit too. But if you lie to yourself, and if we just pretend Polaris is at the North Celestial Pole, for the most part, Polaris is the only star that doesn't really drift around because this is the direction of Earth's axis, and the spin of Earth is what causes the sky to spin, right?
Gotcha. Now I understand why it's your latitude.
Right. It's the only star that doesn't change during the night. Not much, anyway. And that's why historically it's been an excellent tool to use for celestial navigation. You know, what's interesting, Fred, is it's annoying in the southern hemisphere, things are more complicated because while there is a star located approximately at the North Celestial Pole, there is no equivalent star located close to the South Celestial Pole. And celestial navigation in the southern hemisphere is a little more complicated because of that. You can still do it, but you have to track stars for a bit. A whole bunch of this is an artifact of the effect that over time, Earth's axis tilt actually undergoes a wobble called precession, caused by gravitational tugs from the moon. And over a long period of time, over 26,000 years, Earth's North Celestial Pole is actually drifting in space. And so it's just kind of totally random that there happens to be a star located close to the North Celestial Pole. In fact, as I will explain later in slide da-da-dum-dum, it's taking a minute to load here. Where are you? Well, hell, I used to have a slide on the 26,000 year precession. I can actually, Wikipedia has a pretty nice animation if I can't find that. Here we go. Slide 27. Currently, our North Celestial Pole points towards Polaris. But if you wait about 15,000 years, our North Celestial Pole will point towards the star Vega, and that will be our North Star. And if you wait only 7,000 years, our North Celestial Pole might be pointing towards nothing, and there might not be a North Star at that point. So we kind of just happen to live in an epoch of the history of Earth in which we have a North Star, which is kind of cool. Anyways, since we're only like mayflies compared to the precession of Earth, since we're only going to live about 100 years at best, we can just pretend like Polaris is fixed at the North Celestial Pole. And that means we should be able to describe its location using the skills we've developed so far. How do I do that? How do I tell someone where Polaris is in my sky?
Azimuth and altitude.
Very good. We're going to use the horizon system. And I'm glad that we understand that. That means I require an altitude and an azimuth. Can you give me either one of those?
Azimuth is 0 degrees. Altitude is 42 degrees. Oh,
Nice. The altitude of Polaris is equal to our latitude. So in Rhode Island, that would be 42 degrees. The azimuth is 0 degrees because 0 degrees is the same as north. And this is the North Celestial Pole. North being the closest point on the horizon. Very good. All right, let's try a second question. Describe the path of the celestial equator in the Rhode Island sky. This is a more advanced question because the celestial equator is not a mere point. The celestial equator is actually an arc. When describing an arc through the local sky, the right thing to do is to describe 3 points along its trajectory. 2 points make a line on a flat surface, but the sky, the dome of the sky, is a curved surface. So 3 points are more appropriate. The 3 points we might want to focus on, hopefully that you guys can all see that this red horseshoe is the celestial equator, right? The points we'll focus on are the rise point, the highest point that it will reach, and the point where it sets, the 3 orange dots. I refer to them as the rise, the reach, and the set. Since stars rise in the east, I tend to bias my rising to the eastern side of the sky, right? Okay. So answer number 2. It's an arc, and the arc is going to require 3 points. Each point will have its own altitude and azimuth. And those points we'll call the rise, the reach, and the set. Okay. Get that down in your papers. Man, that whole internet fandango really screwed me up today. Okay, peoples. Let's start with the rise. The sooner the better. Who can give me an altitude and an azimuth for this point?
Would the altitude be 0?
Excellent, Vincent. How did you know that? Explain that to the people.
Because it's kind of just sitting on the horizon.
I couldn't have said it better myself. It's on the horizon, its altitude is 0. And how about the azimuth, since you're doing so good? If you're forgetting, Vincent, remember that the azimuth is measured along the horizon clockwise from north. Oops, sorry.
So it would be 90 degrees.
That's right. From north, this is 90 degrees. By the way, we could also, if we wanted to be just kind of loosey-goosey, we could also say east. So either one of those would work. So we could say 90 degrees, or we could say east. In a way, we can express both the altitude and the azimuth in one shot if we had said due east, because due usually means on the horizon 0 degrees. All right, so as Vincent understands things, how about the rest of you guys? Someone besides Vincent chime in here and tell me how to find the altitude and azimuth of this point, the reach.
The altitude is 48 degrees. The
From our
azimuth
diagram. Yep,
is 180.
that's
degrees.
right, or south, because we have to go half a circle to get to that. Excellent. Okay, you guys are impressing me. So we have 48 degrees. That was the alpha angle from the alpha, beta, gamma, delta game. And then we have 180 degrees, or we could easily say south. That is not due south because it's not on the horizon. And then the set point, who's got the set?
So the altitude would be 0 degrees because it's on the horizon again.
Yep.
And then the azimuth would be 270 degrees due west because that's also on the horizon.
Yep. And due west is an alternative. So we can say 0 degrees, 270 degrees or west, and that whole thing is due west. So in a way, there's a way to answer this question in a kind of literary way that captures all of the specificity of the horizon system. You could say something like the celestial equator is an arc that rises, excuse my handwriting here, an arc that rises due east, reaches 48 degrees in the south, and sets due west. This is kind of a cool literary way that very precisely describes the trajectory of the celestial equator with all of the power of the horizon system. It's not ambiguous. If it wasn't for this, we'd have to say silly things like, oh, it's an arc that rises above the pine cone and the tree in my dad's backyard. That's no way to talk. You know, you want to have some sort of hard references here. These are homework questions today. So
Can
we're
you
doing
back
our
up,
homework.
can you back up to the previous drawing?
Sure.
Oh, no, you don't have it, right? Because you erased it.
Well, I can find it or quickly make it. So you mean the alpha, beta, gamma, delta game?
Yeah, I just forgot the degrees. I didn't write that down. I didn't think we were going to.
Oh my gosh, Fred, what were you thinking? That was the whole bloody freaking point.
Now I know.
Fred, you're killing me. Okay, here, look. Let's do this. Oh, wait, let me clear that. Okay. Yeah, I can do this like right quick. Okay. And then how do you change the thickness of the line? I don't know. So this is the part of the sky that you can't see, right?
Yeah, you could, if somebody could just tell me what it was for alpha, beta, gamma, and delta, I'll just write the numbers down.
48, 42, 48, 42. Right?
Thank you.
Yeah, the whole okay, I'm glad that we appreciate that. The whole point was getting them angles. Ooh, yep, okay. So 48, 42, 48, right? This is the angles, 42, something like that.
Got it.
But in general, the 42 is the latitude and the 48 is the 90 minus latitude. This could change if I sent you to Russia or to Tucson, Arizona, right? Okay. What if we wanted to describe not their trajectory? Well, okay, let's try something else. During the course of the night, as stars rotate through the sky, they rise in the east and they set in the west, and they travel on tracks which are parallel to the celestial equator. We could call them star tracks, or we could call them diurnal circles. Let's look at a picture of these diurnal circles here. Just a moment while I scroll ahead. Each of the colored rings that you see here would represent the path of a star at some random position on the celestial globe as it rotated through our local sky. Obviously, up here, this is the part of the sky that you can see. This is the stuff that's below your horizon. The green disk is the ground or the grass, okay? In order to, I would like to sort of clean this up here so that I don't want you guys getting distracted by all this stuff. Okay, look at the colored rings. The colored rings rise in the east and they set in the west, but these tracks are tracks of constant declination. So while we normally want to use the horizon system, altitude and azimuth, it's also important to be able to superimpose the equatorial system on here, because the equatorial system stays roughly fixed as the nighttime sky rotates. So let's take the red ring. The red ring is the celestial equator. What is the declination of the celestial equator?
0 degrees.
Yeah. So this is 0 degrees, okay? Boy, it always irritates me that there's no degree symbol here.
Just before we go any further, I got a little confused. Can you tell me how was it 0 degrees? Like, I'm a little lost right now.
Sure. Just let me do something here. As silly as this is, okay. Let's go back to. Okay. So because of the definition, of what am I saying here? Of declination. We defined declination. Oh wow, that thing is totally stuck there, huh? Okay, guys, I'm doing a right shit job here today. Control. Okay. That's all I wanted to do. I just wanted to. Okay, you know what? clear all these. I can't handle this. Okay, I was trying to label it. I know that the celestial equator is 0 degrees because, Lionel, in the previous lecture, I defined the declination to be degrees north or south of the celestial equator. And as you can see by CEQ, the red line is the projection of Earth's equator, and the yellow line is the projection of Earth's north celestial pole. Is that satisfactory?
Yeah, I kind of did. I kind of confused myself by thinking something else.
This stuff can be confusing, and part of it is just making sure that we're talking to each other and understanding each other. So you keep asking them questions. No big deal. Okay, so if the red ring is 0 degrees, what would you estimate to be the declination of the blue ring? Try to think about declination here, right? I'm really hoping to draw on this picture. So this is 0. Oops, the line's too thick now. This is, the red ring is 0 degrees. What would you guesstimate the declination, degrees positive or negative from the celestial equator? What would the blue ring be?
Positive 25?
Sure. I'm going to say positive 30 for fun, although your guess is a very reasonable guess. But I'm going to suppose that it's 1/3 of the way up. So I'm guessing positive 30. But I think positive 25 was a great guess. How about the purple line?
Positive 60.
Sure. And then at the north celestial pole?
(90°).
Positive 90. Right?
Positive 90 degrees.
Okay, how about the orange ring?
Would that be negative 30 degrees?
Good. The yellow ring?
Negative 60?
And the south celestial pole would be negative 90 down here. Good. Okay, now you can.
Can you draw the angle where you're getting these degrees?
Sure. I'll tell you how I'm guessing them. I know that the red ring is 0 degrees because it's the celestial equator. I know that there are 90 degrees between the equator and the North Pole. So I know that the North Pole has to be positive 90. So far, so good, Fred? You buy all that?
Get it.
So my next line of argument went like this. Well, how many degrees up should this purple ring be? Well, I can't measure it, but I can use my eyeball and say, it looks like it's roughly 1/3 of the way up. So 1/3 of 90 would be 30. You'll notice that our friend who chimed in with positive 25, he wasn't using exactly my logic, but he was using a similar logic where he said, well, it's not 45, so it's got to be between 0 and 45. I'll say 25. And I liked that. Does that help?
Yep, thank you.
Okay. Okay. Let's think about the motion of the sun. Every day, the sun rises in the east and sets in the west. But over the year, the sun is slowly drifting along the path that we call the ecliptic. Here, I'm going to use definition number 2 of the ecliptic. Why doesn't someone read that out to me here? Let me look for a picture here. Here, I've tilted the Earth so that the north celestial pole is yoinked off to the side. I've tilted it by about, I don't know, 23.5 degrees or so. So there's my north celestial pole, where Polaris is. And I've tilted so that the ecliptic, the path of the sun, is horizontal. Honestly, it's not that helpful. It would probably be better. In fact, I think I have a picture where the ecliptic is tilted, where we keep the North Pole pointed up. Let me see if I can find that. That's actually a much better diagram. Yeah, I think here. Slide 91. So each day, the sun is drifting a little bit along the ecliptic, and then Earth does a 360 spin during a day, and the sun appears to rise in the east and set in the west. But its trajectory through our local sky will depend upon whether the date is March 21st, where the sun is here on the spring equinox, or if it's the summer solstice. What's the declination of the sun on the summer solstice? Can anyone answer that question?
It's positive 23.5 degrees.
Excellent, Caitlin. Caitlin knows that there's a 23.5 degree angle between the ecliptic and the celestial equator. So there it's the full 23.5 degrees. The declination on the equinoxes is 0, and the declination of the sun on December 21st will be negative 23.5. So what will it look like during the day when the sun travels through our local sky? Well, we know it rises in the east and it sets in the west. Let's start with the spring equinox. On that day, the sun is pinned, like pin the tail on the donkey, to the celestial equator. Therefore, its path through our local sky should be identical to the path of the celestial equator. In other words, if I go over here to slide 22, someone's might want to mute themselves. On the day of the spring equinox, or also on the day of the fall equinox, the sun will rise here due east, where the celestial equator is, and then it will come up, staying at 0 degrees declination. It will follow the celestial equator. It will peak at, what's this angle again, from here to here?
It's a 48 degree angle.
48 degrees. It'll peak, it'll get as high as it can at noon, 48 degrees, and then it will sink back down to the west, just like the celestial equator does. And each day after that, it will be shifting a little bit more north after the spring equinox as it heads towards the summer solstice, rising a bit higher and sinking a bit higher until it gets to the day of the summer solstice, where it will rise north of east. It will come up to some maximum altitude to be determined, and then it will set down north of west, right? And then it will sort of redo the whole thing again, each day going ring by ring, lower and lower, till it gets to the fall equinox, where it will travel the celestial equator. In fact, you can do some cool things. People sometimes take these cool photographs. One's called an analemma. And here you can see a person photographing the sun at noon every 2 weeks for an entire year. Now, there's a couple of different purposes to this photograph, not all of which I want to get into. The sky is curved on a flat surface here, so the meridian is probably like this. And you can see at noon, the sun drifts a little bit ahead or a little bit behind the meridian at noon. And that has to do with the fact that the sun does not actually travel at the same rate through our sky every day. It's got something to do with the non-circularity of Earth's orbit. You don't want to go there. It gets messy quick, okay? But I want you to notice that the photographer has left the shutter open on 3 particular days of the year, and I bet you could guess what days they are. What day was this, where they left the shutter open all morning?
Is that the summer solstice?
Good. How about here?
Winter solstice.
No.
That's the fall equinox.
Fall or spring equinox. I'm not sure which one they chose. And then this down here is the winter solstice. Do we see that?
I get it now. This shit just clicked.
All right. I like that. Well, then let's see how good you are. Let's try.
No, don't put me in the spot like that.
yeah, you're talking a tough game there, Lyle. I don't know.
No. Oh no. I can't, because I was looking at the numbers. I was like, okay, the numbers get lower the more lower this thing gets.
Look, this stuff doesn't come easy to everyone. You got to work it a little bit, okay? So
I
let's
did.
talk about the path of the sun. By the way, this is also a homework question. In a way, I'm kind of like preloading our homework to make it more digestible, but I think these are also useful things to have in your lecture notes. So,
I have a question.
pardon?
I have a quick question. Before you erased, I didn't get where it said the celestial equinox is an arc, and then I didn't get the rest of it. Do you mind just reminding me what that was?
Oh,
At the
I said
bottom.
the celestial equator is an arc, not equinox, but equator. And I said there were 3 points, and the points were rise, reach, and set. And then the altitude and the azimuth were 0 degrees east, 48 degrees south, and 0 degrees west. Something like that.
Okay.
I also gave you the azimuth of each. That's what you missed. Paige, I'm actually going to do this again. So just to make sure you understand, what is the path of the sun in Rhode Island on the spring equinox? Do we know the answer?
Isn't the path of the sun? Isn't the sun on the spring equinox?
Path of the sun in the local sky.
Do you want like degrees?
Fuck yeah, I do. I don't want you to be like, hey, it's over there and it's kind of going over there. You know, like I want specific, tangible, quantitative information. I want to know where it rises. I want to know how high it reaches. And I want to know where it sets.
Oh. Okay.
Guys, I was thinking this was a softball. Like I thought I put the wiffle ball right on the thing and I put the bat into your hand and I cocked it back. All you got to do is swing.
The rise be 0 degrees east.
Yep. The reach. Guys, the sun is going to drift through the sky before we get through this question here.
The reach, would it be the 23.5 degrees?
Nope.
No, it would be the 48 degrees.
Yeah.
Let me get this.
So what's the reach again?
48 degrees.
That's an altitude. I need an azimuth too.
Oh, the azimuth would be 180 degrees
Or south.
south.
And it sets.
It would be 0 degrees for the altitude and then 270 degrees west or due west.
In other words, it's the same path as the celestial equator. Because it's on the celestial equator, right? Okay. How about the path of the sun on the summer solstice? Rise, reach, and set. I'm basically asking for this. Rise, reach, and set. Same form.
I think the rise is at 0.
The rise is always at 0 because it's on the horizon, right? And what's the direction?
Gonna go. Jesus. I want to say that the reach will be 90 since it's at the top.
Wait a minute. Every point requires an altitude and an azimuth. Suppose I was going to meet you in New York City and I said, hey, let's get a beer. My favorite bar is on 2nd Avenue. Would that be helpful? No, it would not, because 2nd Avenue is really long and there's 10 million bars on it. 0 degrees is not enough because there's a whole bunch of 0 degrees. It's not a unique point because all of this is 0 degrees. But you're not anywhere. You're at an intersection, 2nd Avenue and 37th Street or something, right? So I need to know what the azimuth is for completeness. It rises 0 degrees. Here you can just use a loose direction.
Be east.
Not really. It's not exactly east.
60 degrees.
Well, to be honest, okay, now I'm tricking you all here. Listen, the calculation of this angle is over your pay grade. This angle on a spherical surface is 23.5 degrees, okay? This is also an angle that's greater than 23.5 degrees, but you can't really compute it without knowing the spherical law of sines, and that's over your pay grade. So why don't we just say north of east? It's not exactly northeast, but it's north of east. So 0 degrees north of east. The reach would be what?
Would it be 42 degrees instead of 48?
Pardon?
Would it be 42 degrees instead of 48?
No.
No. Okay.
Let's take a peek. We know that the angle from the southern horizon
Oh, shit.
up to the celestial equator is what? What's that angle?
48 degrees.
Good. We should also know that the angle between the celestial equator and the sun on the summer solstice is what? What's that angle?
Positive 23.5 degrees.
Okay. So therefore, the height, it's really hard to write with the mouse, sorry. The height, the altitude of the sun from the southern horizon all the way up to its reach at noon in the summer solstice should be what?
Adding 48 plus
Go ahead, do it. Just take
23.5.
your calculator and do it.
It would be 71.5 degrees.
Good. So the reach is 71.5 degrees. And the azimuth direction?
Would it be 180 degrees
Yeah.
south?
Yeah.
Okay.
It always crosses your meridian in the south if you're a northern hemisphere observer. And then the set?
And then your set would be, your altitude would be 0 degrees. And then instead of west, would you do like south of west?
Let's look at the diagram again. If
Okay.
the tracks have constant declination, it's not that it rises north of east and sets south of west. That's not what it's doing.
Oh, north of west then.
Yeah, right? Okay. You have to kind of look at the diagram
Yeah.
to convince yourself. Okay, and then we can proceed from there. This is going to be the answer. Basically, I'm doing the answer to some of our homework problems, but I also think that we have to kind of just talk about it. Hopefully this will go a little faster on our homeworks. We'll see.
But when you write it out, would it be like kind of like the same thing? Would it be the path of sun of the summer solstice would rise north of east, reach 71.5 degrees, and set at north of west?
Something like that. Yeah, that would work. And like I said, these are 2 homework problems today. We're going to do them. We're going to regurgitate them. Okay. I need to do one last little module with you, and it's going to be a little bit of an awkward shift. Now that we've thought about the rotation of the sky and how to describe these coordinates, we've talked about the path of the sun. Honestly, I'd like to talk about the path of the moon, but it's a little bit complicated. The moon's orbit is tilted by about 5 degrees with respect to the ecliptic plane. Now, let's just have a think about how weird this is. To project the ecliptic onto your sky is weird. It changes hour after hour and night after night. But if you look at a global sky, here's the path of the ecliptic. And the moon's orbit is tilted by about 5 degrees with respect to the ecliptic. So on any given night, the moon could be anywhere from 5 degrees above the path of the sun to sort of like, wait, why am I screwing this up here? To 5 degrees below the path of the sun. Let's see here. That's the ecliptic. Wait, I know what I'm doing. I need to and just start like over here. Whew. Looks more extreme on one side than the other. What am I doing? Oh, I'm not going to the center of Earth. That's my problem. Right, I'm a stoopy. Okay, so there's a tilt 5 degrees above the and below the ecliptic plane. Okay, so the moon's orbit, since 5 degrees is not a huge angle, usually it's close to the path of the ecliptic. So you'll often see the moon in Sagittarius or Virgo or something like that, similar to the path of the sun, but not exactly the same. We also want to talk about the path of the planets, which also travel along the ecliptic, because the ecliptic is the plane of the solar system. Do you guys know how many planets are visible to the naked eye?
5 of them.
5 of them, right. And all aspects of timekeeping are connected to the sun, the moon, and the planets. Let's see here. I should have some pictures associated with this. Oh, here are the planets. Every now and then you get these special conjunctions at certain years, certain times of the year. That doesn't happen too often, you know. Every decade or two, you might get a alignment where all 5 of the naked eye planets are in the sky at the same time. People take photographs and they make a big deal about this. That means there are 7 astronomical objects that are not stars and 7 days of the week. No kidding, because the sun is for Sunday and the moon is for Moon Day, and Mars is associated with Zutag, and that became Tuesdag or Tuesday. Mercury is associated with the Viking god Woden, so Wednesday is in honor of Woden, okay? Jupiter is literally Thor's day. Venus is for Freitag, the love goddess, and Saturn is still Saturn Day, okay? It's funny how every aspect of calendar and timekeeping is connected to astronomy. The orbits of the planets are confusing because if you watch them night after night, just like the sun, they're kind of pegged to the sky. But if you watch them on subsequent nights, the planets actually drift with respect to the background stars. And that's how the ancient people knew that they were not the same as stars. After all, Mars or Jupiter to your naked eye, they just look like a really bright star. But if you track their positions night after night, you can see them drifting or wandering with respect to the background stars, which are fixed. Now, like the sun, they also make an eastward journey along the ecliptic. And for ancient peoples, they would have said, oh, that's interesting. The planets seem to be kind of traveling on the same path as the sun, so they must be gods, just like Ra, the energy god, is, right? But planets do something weird. Certain times of the year, they stop drifting east and they undergo something called retrograde motion, where they stop, change direction, and for a period of about 2 weeks, they start drifting west along the ecliptic. Then they change their minds and they drift east again. This retrograde loop, as it's called, really screwed up ancient Greek philosophers. They could not understand why the gods were suddenly changing their direction, reversing course, and going back in a different direction again. The desire.
That's why they got this whole Mercury retrograde bullshit, bro.
Right. So when they say Mercury's in retrograde, which actually happens quite often, right? Mercury goes into retrograde
right now. It's until February 14th.
Right.
Supposedly.
One of the things is, okay, so the answer to understanding why Mercury's in retrograde so much is understanding what the explanation for retrograde loops are. So what happened is, let's see here. Let me see if I can grab the right slideshow. Open file location, celestial mechanics. Or actually, it might be in my astrometry lecture. Let me see here. My other astrometry lecture. Yeah. So when the Greeks were trying to understand why the planets went through retrograde loops, they couldn't get themselves out of the mindset of a geocentric solar system. Because to ancient Greeks, they believed that Earth was the center of the cosmos, which was a reasonable thing to assume because it certainly feels like everything is orbiting around us. But because the Greeks thought perfect circles were heavenly and superior to other types of geometry, they only believed that the orbits of planets could be perfect circles. So to jive those, or to sort of gel those two things together, they orbited the planets. They made them orbit on perfect circles called epicycles, and they put the epicycle on top of another orbit and rotated it backwards. That way
Oh,
the
Lord.
planets could be on perfect circles and they could undergo retrograde loop. To them, this was reasonable because it satisfied the requirement that Earth was the center of the solar system, that orbits are perfect circles, and they could clearly see that planets were doing retrograde loops. And they actually made a pretty decent working model of the solar system using this technique. Thousands of years after the Greeks developed this, the model began to break down with time because it wasn't philosophically true. And that's where the badassery of Nicholas Copernicus came in during the Renaissance. During the Renaissance, people had rediscovered the ancient learning of the Greeks, and they were sort of thinking about the problems that the Greeks thought about. And Copernicus was kind of bummed out that the Greeks required so many rotating circles to describe the cosmos. And he also realized that it didn't work because it broke down over time. And he sort of, there's a lot of cool history here that I'm glossing over. His idea was to put the sun at the center of the solar system. And if Earth went around the sun, there would be a very elegant description of retrograde motion. I want to show that to you. Where is that very elegant description? What the hell? How could that not be in here? Wow, I'm stupid. Okay, hold on. Bear with me for just a moment. I have it in my 1010 lecture. Boy, that was a serious oversight. Come on. In my 1010 class, I go through the history with a little more detail, but we don't have time for that because we have bigger fish to fry in this class. Okay. The reason why planets go through retrograde motion is nothing more than just an artifact of Earth lapping or going past the planets in their orbits. So let's say you have the sun, a blue planet that is Earth, and a red planet that's Mars. Earth has a shorter track to orbit the sun, and it orbits faster. So Earth orbits in about 1 year, and Mars takes about 2 years. So Earth is constantly catching up and passing by Mars. In configurations 1, 2, and 3, as Earth catches up to Mars, we can see that Mars is projected eastward along the ecliptic, and we can see Mars drifting in an eastward direction relative to the zodiac constellations of Capricorn and Taurus and all the rest of it. But what happens is when Earth starts to pass by Mars, first we see it projected forward, but at a slightly smaller angle. And then when we line up with it, suddenly Mars starts seeming to drift backwards or westward along the ecliptic. And in positions 5 and 6, as Earth goes past Mars, suddenly Mars seems to be, just from a geometrical effect of optics, we call it parallax, it undergoes a parallax shift, and it's now suddenly projected westward along the ecliptic, which is just an artifact of us passing it. And then as both planets march along in their orbits, eventually it kind of just goes back to drifting east again, because we start to notice as we get farther away, we see the planet kind of shifting east again. This also happens with inner planets by the same method. But one of the reasons Mercury is constantly in retrograde, messing up the computers, that must have been what happened today, okay? It turns out that retrograde Mercury was just Cox deactivating my internet because I downloaded too many movies last night. All right, anyways, so one of the reasons Mercury goes into retrograde so much is because Mercury's orbit is a lot shorter than that of Earth. It goes around the sun like every 3 months, right? Or it's 0.4 years, I think. So every 3 months, Mercury's in retrograde because Mercury is passing by Earth in orbit, right? It's really silly. Actually, you'd think if they were going to choose a planet to mess you up for retrograde, they would have chosen one like Pluto, which, you know, or maybe one like Jupiter, actually, which goes into retrograde the least. Of course, they had to choose Mercury because they're negative Nellies and nabobs and want a lot to complain about. Anyways, although Copernicus's model of the solar system was great at describing retrograde motion, Copernicus actually suffered from the same flaws, the same exact flaws that the Greeks did. Copernicus believed, probably because he spent some time reading Plato, that the orbits of planets had to be perfect circles. And because of this, his model suffered. And even though his model was good at describing retrograde motion, he had trouble convincing modern scientists that the sun was the center of the solar system. In a way, it's kind of similar to this whole anti-vaxxer thing that's going on now with COVID, where somehow this obstinate group of people just don't want to believe that vaccines and science works. And once you get a certain enough people against a thing, they will constantly find all these conspiracy theories and reasons to believe it. And Copernicus is, and there probably are reasons why someone didn't do a good enough job explaining the vaccine thing. Copernicus, by choosing perfect circles for his orbits, left the room for doubt for, let's call them anti-heliocentrists, to believe that the sun was the center of the solar system. It took another scientist 100 years later, Johannes Kepler, to understand what the real problem was. The problem wasn't putting the sun at the center of the solar system, it was using perfect circles for the orbits of planets. And that's where our friend, the last thing that we need for our homework today, Johannes Kepler was a German astronomer who actually designed the first correct working model of the heliocentric solar system by relaxing the restriction that planets had to orbit on perfect circles and by modeling the orbits of planets on ellipses. Now, I'm sort of out of time, so I'm going to have to sort of start next time's lecture on this. But although it's going to be a little bit awkward, Kepler came up with some mathematical formulas to describe the orbits of planets. And I intentionally made 2 of our homework questions today based on Kepler's laws so that it would force me to push this class forward into the Orbiton chapter. So let me just take one little bit of notes here and we can make them better next time. But I just want to give you a couple of formulas to help us muscle through our homework. So just think of this as a sort of precursor to next Tuesday's lecture, since it's going to be a little awkward. So Johannes Kepler was a German astronomer, also a mathematician, but we'll keep it simple. And he was working, I don't know, 1650 Common Era or AD, however you like to do it. All right. And he was after Copernicus, and he modeled a Copernican solar system using ellipses for planetary orbits. I've already hinted around the fact that Earth's orbit around the sun, the ecliptic, is not a perfect circle. And ellipses are a kind of squishy circle where the sun is located here at a so-called focus point. And the planet kind of orbits around with a closest approach called perihelion and a farthest approach, well, let me redo this quick diagram here. Where's my eraser? Here we go. Aphelion. I'll put the planet up here. The planet is usually orbiting counterclockwise, right? And Kepler gave us a set of 3 laws of planetary motion. Now, I'm not going to do all 3 laws today because it would take probably about 15 or 20 minutes and I'm kind of out of time. But I want to give you a couple of quick formulas related to Kepler's laws of planets. So I'm just kind of slapping them up on the board. We're going to use them on our calculators and learn how to punch the buttons and we'll save the understanding for next time. One formula is called Kepler's third law of planetary motion. Very useful formula in astronomy. And the law is p squared is equal to a cubed, where p is the period of the planet measured in years, and a is the distance to the planet measured in astronomical units. That's the quick and dirty version. And that's, of course, distance from the sun, okay? It's actually the average distance, but the other formulas we're going to need today let us calculate perihelion and aphelion distances. But they require us to understand that there's this parameter E called the eccentricity. The eccentricity can be thought of as the percent squishiness of the orbit, where E is a parameter that can be anywhere between 0 and 1, but not 1. So it's basically, if E is 0.5, you have a 50% squishy orbit or something like that. And the other formula that I want today is the formula we need to calculate perihelion and aphelion distances. The perihelion distance is a times 1 minus the eccentricity. The aphelion is a times 1 plus the eccentricity. So obviously we need to talk with a little more depth, and we need to go over these details a little better. But honestly, I just wanted to slap this into your notes so that we can muscle our way through our homework today. And on Tuesday's lecture, I will properly introduce Kepler's laws of planetary motion, and we'll make a nice diagram of an ellipse, and we'll go over this stuff really carefully. But for now, why don't you think of it as today we're going to practice how to punch the things into our calculator so that you know how to find your square key and your cube key, okay? Okay, so today got off to a rough start because of my internet issues, but somehow I actually managed to cover just about everything that is going to appear in our homeworks today. Our homework today is going to be a little bit crunchy, one of the crunchier homeworks that we have to do. But by giving you some of the answers during the lecture, I'm hoping that that will speed things up. We'll see. It's customary for us to take a little 5 to 10 minute break just to chill and have some tea or coffee before we go forward. Is everyone down with that? All right. So iPhone time is 1:07. Let's give ourselves to, I don't know, 1:20? Start at 1:20? That's the plan. Okay, see you then. Welcome back, Astronomy 1020. We're about to do homework number 2. Let's open up our Blackboard page and let's get the questions queued up because I'm going to want you guys to do some reading. A number of different announcements that I'd like to make. A little behind on the homework grading. I did finish the AS1020 grading yesterday. I'm going to tackle you guys after class today, so just bear with me. I'm a little behind. It happens. Go to homework on your Blackboard page. We're doing this problem set here. You might want to right-click and open up these PDF questions if you do not have a textbook. And please have these handy. I'm going to ask you to repeat them to me in just a moment. As we did last week, we will format the same way. We'll put our names down. We'll put AS1020. Depending on what your section is, you'll either write 001 for the day class, 102 for the night class, or 600 for the online distance learning class. And the homework today is homework number 2. It's problems from different chapters. I think there's a problem from chapter 2, problems from chapter, well, geez, what do we got here? One problem from chapter 2, 2 from S1, and 2 from chapter 3. Can you guys read them off to me?
S1 is 41 and 43, I believe.
And chapter 3?
Chapter 3, hold on.
53 and 54.
Okay. The last two are actually the easiest one today. The first three are a little bit more time consuming. Okay, so let's launch right into it. Chapter 2. Oh, I should also mention, I keep forgetting to say stuff. I have to do verification of enrollment. Anyone who does not turn in any lab or any homework will be marked as a no-show, and they automatically drop you from the class. That shouldn't be happening to anyone I'm talking to here because you're already doing your homework. But I should mention that it's important that we turn some stuff in. Chapter 2, number 59. I need a reader here. Caitlin, you want to take us away?
Yeah, I can do it.
What's the title?
The title is Eclipse Conditions. And the first part is the moon's precise equatorial diameter is 3,476 kilometers, and its orbital distance from the sun varies between 356,400 and 406,700 kilometers. The sun's diameter is 1,390,000 kilometers, and its distance from Earth ranges between
Hey,
140
1,390. That's 1.39 times 10 to the what?
the 4.
Nope.
No. 6.
Okay, cool. And what about its distances?
Its distance from Earth ranges between 147.5 and 152.6 million kilometers.
So that would be times 10 to the 6 in each case, because million
Yeah.
is times 10 to the 6. Remember, any number that's greater than a million has to be in scientific notation. Okay.
And then part A is find the moon's angular size at its minimum and maximum distances from Earth.
Let's draw the picture here, guys. We have, my circle maker is not great. Let me see if I can do this again. Because I'm there we go. So here's our moon. And I want you to draw this picture. The moon has a diameter, which we are going to call S. We are looking at it from some distance away, which is changing as the moon's, this is related to the last part of our lecture, guys. The moon's orbit, just like the Earth's orbit, is an ellipse. And because of that, it has changing distances. In the case of the sun, we call it perihelion and aphelion. In the case of the moon, we call it perigee and apogee. But it's the same concept. It's the distance between the moon and the Earth is varying. This is a problem that uses the small angle formula, which relates the angular size of the astronomical object to its physical size S and its distance D. Last week, I told you that the small angle formula relates these three quantities by S is equal to theta times D times 2 pi over 360. What's actually happening is, in this case, they are giving us the S and they're giving us the D, the changing distance, and they're asking us to solve for the angular size. Now, if we do a little algebra, we can flip the 360 over 2 pi to the left and divide by D, and we can solve this for the angular size. And then the formula looks something like this. The angular size of our object is 360 degrees over 2 pi times S, the diameter, divided by D, the distance. Very useful formula to have written down. Yes, friend, this will appear on your formula sheet, and you will be doing questions on this, which is why this problem is a great practice, because you're going to be doing it 4 times, once for each distance. Take a second to get all that down nice and careful, because I'm going to have to erase. This is all of our data.
The little symbol with the, that's inside the angle, the circle and the little line going through it.
Yep.
What's that called?
It's called theta, but who cares? It's also angular size. Now, if you want, you can know its Greek letter, theta, but really that symbol represents the angular size of our astronomical object. You know, there's names for all these Greek letters. Maybe you've heard of this one called Omicron before, you know? Here, I've got Greek letters in my little, you know, this is a treasured item when I was a student, my pocketbook of integrals and mathematical formulas. Noid. Okay, noid alert. But something it did have that was quite useful is all the Greek letters and how to pronounce them. That was useful. So theta's right here. There are lowercase and uppercase versions. So I guess after Omicron, we can be expecting the pi variant. Whoa, the pi variants to come and get us. Okay, maybe we'll have another furlough here at home.
I guess the other concept and understanding, because if I'm looking at the moon drawing and the 2 lines next to it, it says S, but isn't that the diameter of the moon?
Yeah, so I'm sorry, what's the problem there? I somehow missed your point.
All right, so the diagram you have with where the person's looking at the moon, right?
Yep.
And on the right-hand side of the moon, you have 2 lines up above it, and like at the top and at the bottom.
Yep.
And you have an S, but isn't that the diameter of the moon?
Yeah, but I didn't want to use D for diameter because I'm using D for distance.
Oh, okay. I got it.
So as I mentioned before, S is size and S is also diameter. Sometimes we use funny letters for things, you know. To answer Emma's question, Emma's like, hey, where can I get one of those? Well, Emma, yes, I love this thing. And it's got all these cool, helpful formulas. I'll tell you where you can get one. I actually found this, like, at some point they had it online. Yeah, okay, Emma. Hey, Emma, I'm about to hook you the hell up. Let's see if I can do this. Emma, you have no idea what I'm about to do here. Let's go to this PC. Let's go to, where's my Dropbox? None of this is making any sense to me. Sorry. Why doesn't this look right? Share a file. And, ooh. Come on. Where's my damn Dropbox? I'm having trouble. Can I search? This box is so tiny. It wouldn't be in downloads. It wouldn't be in documents. Library. I just want to go to the damn. Oh, there we go. Okay. Would it be under books? Pocket formulas. Oh my gosh, look at this. Check that out, Emma. You're welcome. You have one now. In fact, this is the second edition. I think that's like the 5th edition. It's even better than this one. Cool. Yeah. You too can have a table of pocket formulas like mine. Actually, this was so handy to me as a science student. I wouldn't have survived without it. It's so wonderful. And so, you know, don't be afraid to get noidy. Love this thing. Okay, let's get to business here. I'm getting distracted. I'm going to erase. Does anyone have an objection? All right. So continuing on, chapter 2, 59, let's make this nice and neat and organized. We will start with the moon. We are going to solve for the angular size. It says nearest and farthest distances. So first we'll do perigee, which is the closest distance. The angular size would be 360 degrees over 2 times pi. What is the S for the moon?
It would be the diameter, which would be 3,476 kilometers.
Nice. And what's the closest distance at perigee?
The closest distance at perigee would be 356,400 kilometers.
Okay. Now, if you write it like this is how you set it up. And I think I had to chastise a few people who did not set up their problems the way that we do here. You should be doing exactly what I do on the board, or I will deduct points. Now we have to talk about how to punch this. How many people have calculators? Show me. Show me your calcs. Good. Good. Everyone here knows how to party. Listen, this is tricksy, okay? Let me talk about how we're going to do this before we do it with my cat laser, okay? We are going to type in 360. We are going to divide by 2, but we will not hit times there. We are going to divide by 2, and then we will divide by pi so that the calculator knows what's up. Then we will times it by this, and we will divide by that. Anytime something is in the bottom, you hit divide first. So watch me and follow along very carefully with me. I'm going to move quick here. $360 divide by 2. Now the EXP is pi, so I'm going to do divide by EXP for pi, then times 3476, then divide by 356,400. At the end, I hit equals. Show me what you got. Everyone hold up their calculators. I want to see that you got the same number I did. David is good. Fred's good. Mikey's got it. Caitlin's got it. How about the other guys here? Vincent and Dennis. Oh, Dennis is using
Oh,
a
I
best.
did something wrong. I don't even know what I did.
Oh, Dennis, I'll tell you what you did wrong. First and foremost, you're not using the fucking Casio FX260 solar. And that's your first wrong. Oh, no, but I got this. I know what I'm doing until you don't. So, Dennis, now that you've screwed up real time, will you please go out and spend the $10 on a Casio FX260 solar? Please. Could you do that for me?
Yes,
It would
I
mean a
will.
lot to me as a friend. Okay, meanwhile, since you're a special person, you're going to get your own special instructions. Hold the calculator up and let me see what you did. See, this is the kind of shit I want to avoid doing. Hold it up, hold it up, hold it up. I don't care. Just, no, go second entry. There's a button. You don't know how to use that thing, do you? There's a button called second entry, which shows your last input.
No, that's normally with this one. I just have to press the up thing, but when I clear it, it gets rid of it.
Okay, so So then do what I said, do 360, divide by 2, divide by pi, times 3476, divide by 356, 400. Don't use any parentheses, just divide, divide, divide.
Not. Okay, wait. Fraction. All right. 3, 4, 7, 6, 3, 5, 6, 400. Oh, now I get this. I put it all in at once and I got the right number.
All right, yeah, I don't like anything that's happening there. Please get a Casio. Get that out of my face.
Okay.
Okay,
I will.
so how many sig figs should we keep?
3,
Where do you get that from?
the 360 degrees.
360 is a perfect number.
Okay.
It has infinite precision. Let me explain to you. Suppose I told you that the radius of a circle is half its diameter. That would make sense to you, right? But if I wrote it as a mathematical equation, radius is half the diameter, that too is not a measurement. It doesn't have precision with it because it's conceptual. We know that a radius is exactly, precisely 1/2. It's a conceptual idea. There is no measurement precision associated with 360 degrees because there are exactly 360 degrees in a circle.
Okay, so
These, however, are measurements.
then it would
Because
be 6 figs.
how many?
4.
4. Top has 4, bottom has 4, you keep 4. So tell me what my final answer should be.
It would be point.
First of all, always put the lead 0 out front, even though it's not significant.
Yeah, so it'd be 0.5588.
Good. And the units?
Would it be? Would be theta, right?
Well, theta is the variable, but the units are what?
Degrees.
Yeah, that's all that's left. It is an angle, so that makes sense. Okay, let's do the second verse, same as the first. Apogee. The angular size is 360 degrees over 2 pi. The diameter doesn't change. It's still 3476. But what's the distance now? Quick.
406,700 kilometers.
Okay, you know what you're doing, Dennis included, so punch them up. I don't want to have to punch this for you every time. 360 divide by 2 divide by pi times 3476 over 406,700. Hopefully I didn't get any of those numbers wrong. What'd you get?
It'd be 0.4896 degrees.
Hold on, you are under obligations to round properly. The number after 6 is 9. So what are you going to do?
Oh, it'd be 797.
Okay. Oh, by the way, that's part A, right? Let's label this properly. Now it's on to part B. Part B is the sun. First, we will do perihelion. Formula is the same, numbers change. 360 over 2 pi times 1.39 million kilometers over, what was it? 147.5 million, is that it?
Yeah, that's right.
Okay, this time we're going to use our EXP key wherever we see times 10. Use the EXP or plan on getting it wrong, Dennis, okay? And friends, so this time I'll punch one more time for you, okay? 360 degrees, divide by 2, divide by pi times 1.39 exp6 divide by 147.5 exp6 equals. What's my answer? Hold up your calculator. Show me that you did this. Yep. Fred's good. Vincent's good. Who else? Show me what you got.
Wait, what was the not the numerator, the
You've got this-
denominator?
Thank you,
One
Mike.
plus one.
You've got it written down on your paper there. That's the
No, I
closest
forget
approach,
it.
and that's the diameter of the sun.
Okay, I got it.
You got it, Dennis? Okay, you're using your double E key, right? Or your E key, whatever it is.
I don't have one of those. I have a button where I can manually put in like what I want it to be.
No.
Wait, but it works. It works. Look, I got the same answer as you.
Dennis, you're assuming because it worked once that you're good.
It
Now,
worked for the other
now I
two
want you to
people.
listen to me. You can feel free to ignore me, and then you will have a new discovery somewhere down the river, okay? It's not going to work forever. You're going to screw up. And this is not the last time I'm going to have to deal with you. Hold your calculator up to the screen, please. Just hold it up. All right, now slide it up a bit. Slide it up. No, the
Slide
other
up.
direction. I want to see
Oh.
the buttons. I want to see your buttons.
Oh, my buttons.
Show me your buttons. A little closer. Oh, that calculator sucks. You have
I have everything. This calculator has everything I need.
all right.
Oh,
Well,
wait, I do. I even do. Look. I have that and
yeah.
and
From now on, you use that key.
that
Okay.
one. Right.
You gotta trust me on this, Holmes. You're
I
gonna
will. I
you're
will.
gonna run into trouble as we go crazier. Like it's gonna happen. Okay, what's my answer?
Zero point 5399 degrees.
How many sig figs can I keep?
Oh. Jesus, I don't know. 3?
That's right. So round it.
Oh. 0.4.
Nope. 0 point.
Oh, 540
Good.
degrees.
Excellent. All right, and aphelion. The angular size is 360 degrees over 2 times pi. Same diameter, 1.39 million kilometers. What is it? What's the farthest distance?
152.6 times 10 to the 6th.
Okay, punch them up. 3 sig figs. Answer?
It would be 0.522 degrees.
Nice. Now we're rounding proper. I like it. There's one last part to this, which is part C. What does part C ask?
Based on your answers to parts A and B, is it possible to have a total solar eclipse when the moon and the sun are both at their maximum distance? Explain.
Which one is the maximum distance again?
So your maximum distance for the moon is 400.
Apogee.
400. Oh, yeah.
Notice that the maximum distance is the minimum angular size, which makes sense. Farther away is a smaller angle. Is it possible to have a total solar eclipse?
I would assume so.
Oh my gosh, I'm not plugged in. Oh my gosh. How did that happen? How did I get away with this? Whew. If this had gone kaputs, I would have lost my video. Wow. I can't believe I made it through tea break and everything. That's crazy. Okay. Sorry. What did you say? You suppose so?
I would assume so, yeah.
Okay, but we're not looking at the numbers here, bud. Let's round these to 2 sig figs, right? The angular size of the moon is what to 2 significant figures?
It'd be 0.49 if you rounded it.
Degrees.
Degrees.
And how about the sun?
That would be 0.52 degrees.
So what would that look like? Okay. Let's see here. The angular size of the sun (0.52 degrees) is larger than the angular size of the moon, do you see?
Yeah.
This is not a total solar eclipse. This is a special type of an eclipse. I thought I told you about it. Did we talk about this?
Is it an annular eclipse?
Yeah, that's right. Sometimes the angular size of the moon shrinks to just under half a degree. And instead of in a total solar eclipse, maybe we need to look at some pictures here. I showed them to you before. In a total solar eclipse, the disk of the moon completely covers the disk. The disk of the moon completely covers the disk of the sun. Now, all that peach fuzz that you see around there is the corona. That's a outer wispy layer, but the main circular disk of the sun, its photosphere, is being blocked. Here you can see we're just about to slide over during a total solar eclipse. And you can, lame. Okay. In any case, the type of an eclipse that we have is not a total solar eclipse, like you see here. It's an annular eclipse. So the trick, Caitlin, was to actually look at the numbers. And annular eclipses create this kind of, they call it sometimes the ring of fire. It's where the full disk of the sun is not blocked by the full disk of the moon. The angular size of the moon is in fact, according to our calculations, it's 0.03 degrees smaller, which is a noticeable angle to the human eye. So the answer, which we should write down, should go like this. No, a total solar eclipse is not possible at max distances, and I do mean to say distances because they are both need to be at maximum distance, because the angular size of the moon is 0.03 degrees less than the disk of the sun. Instead, you get an annular eclipse. And that's 59. I'm ready to erase. Fred, are you still writing? Or are we good?
I still need to write.
Who was just saying I need to write?
Emma.
Emma, will you let me know when you're done?
Yeah, I'm almost done. Okay, I'm good.
I'm erasing. All right, Fred, are you down to read one? Sorry, Fred. Is that a yay or a nay?
Not really.
Oh, well, you're conscripted anyways. How about that? So, chapter S141. What's the title?
Hang on, I gotta get to that book thing.
Yep,
I think I had the wrong one open.
it's homework 2. We'll make sure you don't, because we want to make sure we're turning this into the proper place, right? That could be an issue.
Okay, what number is it that we're looking for?
S141.
Damn, where am I? Hang on, I gotta go back to it. Oh, S1. And then question 41?
Yeah, fundamentals of your local sky.
Okay, got it. Fundamentals of your local sky. Answer each of the following questions. No, the following for your latitude.
Okay, just pause for a second. So, fundamentals of the local sky. What is our latitude, Fred?
I have no idea.
I told you in the lecture, this is important. Look it up in your notes.
42 degrees.
42 degrees north. A latitude should always include, by the way, guys, I'm not even trying to hide this from you. I'm going to give you questions about latitude, and I'm going to give you the same angle, and one's going to say north and one's going to say south. So you better be able to discriminate. Okay, what's A ask?
Where is the north or south celestial pole on your sky?
What is in our sky, the north celestial pole or the south celestial pole?
The north.
Good.
Celestial.
So NCP in the local sky. Does anyone know how to do that?
It would be our altitude and azimuth, correct?
That's right. We're going to use the horizon system. Excellently done. I like it, Caitlin. You went right to the horizon system, just as you should. So what do we do?
Would you have to calculate the rise, reach, and set, or would you just want 1 point?
Well, I guess that's a question I'm going to flip right back to you. Is the north celestial pole an arc or is it a point?
Oh, it's just a point.
So it sounds like one altitude azimuth will do.
Yeah. So
And it sounds like it's this point right here.
yeah, so it would, so your altitude would be 42 degrees.
Excellent.
Our azimuth would be 0 degrees.
That's right. It's 42 degrees, same as Polaris. And its azimuth is north. And north is what? Sorry, what
North
did,
is, I'm sorry, say that one more time.
actually, I forgot what you said. What is the azimuth?
The azimuth is 42 degrees north.
No, an azimuth of 42 degrees north would mean starting north
Oh,
and
I'm
swiveling.
sorry. I thought you said altitude at 0 degrees.
That's right, because 0 degrees is pointed due north. Okay, cool. Excellently done. So our altitude, 42 degrees, and the azimuth is 0 degrees or north. Cool. What's part B say? No, you guys were much faster because of the good work we did during lecture today. I'm liking this.
I forgot to unmic myself. Hang on. All right. Describe the meridian in your sky, specifying at least 3 distinct points along it, such as the points at which it meets your horizon and its highest point.
So where is the meridian on our local sky?
It's the celestial equator.
Nope. What's up with the meridian? Hey, you guys are allowed to draw on this picture, you know. Why don't you choose annotate and show me where the meridian is with your pencil? You can click the annotate button and you should be able to draw just like me. Who's got the guts to show me where the meridian is? Oh, is that you, David? Oh, who did that? Sometimes it'll tell you who's drawing. Who's purple?
That was me, Vincent.
Oh, hey, Vincent. Hey, good job. Vincent knows exactly where the meridian is. It's a north to south arc. So, Vincent, I guess our 3 points could be here, here, and here, right?
Yes.
You got the guts to tell me what the altitude and azimuth? Why don't we start with, let's start with this one. Now, stars rise in the east and set in the west, but I have a north to south bias because that's just how I am. So why don't we start with our northern point?
Okay. So for the northern point, the altitude would be 0 degrees.
Okay. Actually, let's format it like this. Let's do altitude and azimuth, but we're going to have 3 points. We're going to have a rise, a reach, and a set. For the rise, what do you have?
0 degrees. Or
Yep, it's on the
north.
horizon.
And then the azimuth would be north.
Good.
Or 0 degrees again.
Let's put both versions down because I think that'll help us learn.
Next, the reach, the altitude would be 90 degrees.
Good. The azimuth?
What?
The azimuth?
The azimuth, would that still be 0?
Vincent, this one was tricky. Let's take a look at the drawing together. The idea for azimuth, Vincent, is that if you have a random point on your sky, you try to figure out where the closest horizon is, and then you start north and you like swivel clockwise until you get to that closest point. So far, so good?
Yeah.
But now consider this, Vincent. Here at this point, which is your zenith, every single place on the horizon is equidistant in angular space from the zenith, right?
Yeah.
There's kind of like no one preferred horizon point because every single point on the horizon is exactly the same distance or angle from the dot, right?
Yeah.
Would it be undefined then?
Yeah, this is a degenerate point, just like we had for the longitude of the North Pole. You might remember that. Sometimes you have coordinate. Now, the reason why that's okay is because if you specify an altitude of 42 degrees, that is not a single point, but this entire ring, all that ring has an altitude of 42 degrees, because any point on that ring is a 42-degree angle from the horizon, right? But once you get to the zenith, an altitude of 90 degrees can only be one place on the local sky. That's your zenith. So it's kind of okay that it breaks down, but you have to first recognize that azimuth is undefined. We could put afterwards at the zenith. So just like there's a fancy term for this is due north after all. And that's the zenith. And then where does it set?
Oh, it sets the altitude is 0. And the azimuth is 180 degrees or south.
Excellent. Vincent, you're doing good. This stuff takes a little while to click. So if you're not getting this as quick as Vincent, don't stress. It takes a little while sometimes for all this to lock into place. You got to practice, practice, practice. I'm ready to move on to part C. Can I erase? Emma, friends, can I erase?
Yeah, I'm good.
I believe part C, Fred, is the celestial equator, right?
Describe the celestial equator in your sky, specifying at least 3 distinct points along it.
I was thinking this one would be easy, right? I mean, normally it's not, but. Why do I expect you to know the answer to this?
We did it in class.
Hell yeah, I was testing you to see if you understood that. Rise, reach, set. We already did this today. Tell me what we've learned.
Your rise would be 0 degrees.
And
Your azimuth would be 90 degrees east or due east. Your reach would be 48 degrees. And your azimuth would be 180 degrees south. And then your set would be, your altitude would be 0 degrees. And then your azimuth would be 270 degrees west or due west.
again, if you're one of those people watching later who skips the lecture and just goes right to the homework, nice job. You can go back and watch the lecture and learn how we got that. D, Fred, I'm erasing.
Does the sun ever appear at your zenith? If so, when? If not, why not?
What do we think?
You would compare the two then.
I'm sorry, I do what?
You would compare the rise, reach, and set of each and see if it does, correct?
Each what?
Each
I'm with you.
each altitude and distance.
But for what is varying from each to each?
The degrees
Of what?
of altitude. I don't know that.
Oh, like, how do you know that we're comparing? How do you know we're comparing something if you don't know what we're comparing? Like, in other words, I think you're right, Caitlin, but I think you're missing some phrases here that I need to hear. Does anyone know the answer? Maybe you need a hint. Slide 22 might give you a hint.
Is it because it's relative to where you are?
What's it?
The Rhode Island of the sky.
Sun?
The sun.
Yeah.
So we're comparing the sun and we're comparing it from what to what? I don't think, does anyone understand me?
I didn't really get.
What are we doing here?
We're comparing the sun's path at the solstices and the equinoxes.
Hell yeah. Now you're talking. You're comparing the sun at different days of the year. Who said that just now? Who was talking to me?
Vincent.
Vincent, if there was ever a day when the sun might hit my zenith, what would you expect that day to be?
Sometime after the summer solstice.
Well, hold on. After the summer solstice, it goes back down again, right?
Yeah, sometime around then.
Yeah. In other words, the day when the sun actually gets highest in my sky is at noon on the summer solstice, right?
Yes.
Because any other day it's going to be lower in the sky. So I guess what we should do, Vincent, is figure out how high the sun will be in my sky at noon on the summer solstice. And then I'll know if he even stands a chance of hitting the zenith. So how high is that? What's my answer? I want to know what is this angle.
You want the reach of it?
Sure.
Would that be 71.5 degrees south?
Excellent. And you knew this because you knew that the angle of the celestial equator, which I'm pointing to in orange, was 48 degrees from south. And you know that the sun can drift anywhere from 23.5 north to 23.5 south of the celestial equator. So what's the answer to the question?
No, it doesn't.
No. The sun will never reach the zenith in the Rhode Island local sky, but only reach a maximum altitude of, let's show how we got it, 48 degrees plus 23.5 degrees equals 71.5 degrees in the south. This is going to be all these prepositional phrases. In the south at noon on the summer solstice. And any day, it will always be at a lower altitude if it's not noon, and it will always be at a lower altitude if it's not the summer solstice. Hey, today, what's the date today? January 27th?
Yeah.
Suppose I looked up the declination of the sun. Maybe this is too much for you guys, but it's not too much. It's just a little bit, it's basically the same question. If the sun today has a declination of minus 18 degrees, can you tell me what the max altitude of the sun was at noon a couple hours ago? Celestial equator is 48 degrees minus 18. That's the declination. The sun got to a maximum height of 30 degrees today. Psst, that's why it's fucking cold out. Okay, because there's not as much direct sunlight shining on Earth. It's hitting the Earth at an oblique angle and it's being spread out. Less energy per square foot or per square meter. What am I saying here? Okay, thought question. What is the maximum latitude you could go on Earth and still have the sun hit your zenith? What is the maximum latitude on Earth at which the sun would still hit your zenith?
Would it be a declination of plus 60 degrees?
Hold on, declinations are for the sky. I'm asking about a latitude. I'm saying, what's the maximum latitude on Earth you could go to? Let's try a different slide. Let's try slide 91. No. Damn it. Thought I had this picture somewhere. What is the maximum latitude on Earth that you could go and still have the sun be at your zenith at noon on the summer solstice?
Is it just 0 degrees?
No, 0 degrees is on the equator. The sun will definitely hit your zenith if you're on the equator. But as you get more north, it's less likely. Up until what latitude?
Would it be 23.5?
Degrees north, also known as the Tropic of Cancer. And the sun can also reach your zenith as far as 23.5 degrees south, also known as the Tropic of Capricorn. That's what makes the tropics the tropics. They're places where the sun can cross your zenith at noon and burn your butt off. That's why they're very hot, right? Just something to think about. All right, part E.
What range of declinations make a star circumpolar in your sky?
Okay. Here's a quick rough and ready definition of circumpolar stars. Circumpolar stars never rise or set. There's a lovely photograph of circumpolar stars in the textbook on page 24. It's the opening chapter. Oh, wow. Opening chapter. Opening photograph of chapter 2, sorry. Some clever person took a photograph of circumpolar stars as seen from the Grand Arches National Monument in Utah. And look what this clever person did. They set up the tripod of their camera at just the right distance so that Polaris appears at the center of the arch, and you can actually see circumpolar stars inside the arch. They never rise or set because they're too close to Polaris. Now, the stars outside the arch are orbiting Polaris, but they're not circumpolar because these ones set below the horizon. We're looking for the range of declinations that would be circumpolar in our sky. Now, first of all, let me speed this up because this question is already taking a while. Keep in mind what the range of declinations are for the entire nighttime sky here. Declinations start at the celestial equator at 0 and they are measured up to positive 90 at the north celestial pole and down to negative 90 at the south celestial pole. Declinations are your degrees positive or negative from the celestial equator. But also remember that we are on our local sky view because we're looking from Earth. Slide 48. Ah, shucks, I'm sorry, here we go. So this as a declination of 0 degrees. This is a declination of positive 90 degrees, okay? That's declination. We know that Polaris is circumpolar. It's kind of the ultimate circumpolar star. And the stars really close to Polaris are also circumpolar. A range of declinations means 2 numbers, okay? So our answer should look like this. From what to what can declinations be circumpolar? With a minimum and a maximum value. Can anyone fill in either of those numbers for me?
Would the maximum be 90?
Positive 90. Thank you, Vincent. I was
Positive
hoping that
90.
would be instantly obvious because there is no declination greater than positive 90, and Polaris is at positive 90 and it's circumpolar, right, Vincent? Okay, Vincent, since you seem to have a little bit on the ball today, let me try to press you a little bit further if I can. Let's think about where the last circumpolar star is on our sky. Polaris is circumpolar and that's circumpolar, but it looks to me like the last circumpolar star is maybe one of these two right here, right?
Okay, yeah.
Vincent, what makes this the last circumpolar star? What's it doing that no other star is doing?
It's not setting.
Right, but these aren't
No.
setting either. But why is this one the last circumpolar star? It's doing what?
It's arcing. It's not completing a full circle.
It is completing a full circle. It has to be circumpolar. These do not complete a full circle.
It's touching the horizon.
Thank you. Now someone's with me. Who's talking there?
Emma,
Emma, it's touching the horizon in which direction? How would I know what direction this is?
Maybe
Here's-
clockwise.
It's orbiting actually, stars rise in the east and set in the west. If you're looking south, they actually orbit clockwise during the day. Isn't that fucked up? So if you're pointed north, they do. Okay, fuck, I just gave it away. Guess what, Emma? This is north because that's where the North Star is, okay? The last circumpolar star is the circumpolar star that grazes your northern horizon. So the very last circumpolar star is the one that has an orbit that takes it right there. Now, you know the declination of the celestial equator. It's 0 degrees. You also know the declination of the north celestial pole. It's positive 90. Which one of you clever peoples can tell me the declination of that point? Your northern horizon has a declination. Every point on your sky should have a declination.
It's 60 degrees, right?
No.
No.
Would it be 0 degrees?
0 degrees altitude, but that's not declination. Declinations are measured from the celestial equator. 0, positive 90,
positive 135 degrees.
there is no such thing as positive 135. Declination goes from plus 90 to minus 90 and not above or below. But I think you're getting warmer now. Now you're getting warmer. Let me give you a better hint. These are tracks of constant declination here. So try again. This time, you're trying to find the declination of that point and we measure it from the celestial equator, right?
Oh,
Mm,
negative 45 degrees.
No. Negative declinations are all below the ring in that direction. You are above the ring here.
it'd be positive 42 or 48 degrees.
Which one?
48.
Very good, because the altitude of Polaris is 42, right?
Mhm.
Which means this angle has to be positive 48, right? That was tricksy. Positive 48 to positive 90. All right, read part F.
See, I'm muting, it gets me. All right. What is the range of declinations for stars that you can never see in your sky?
Now, I call them anti-circumpolar stars. I don't know if other astronomers do that, but sometimes they still call them circumpolar, but I call them anti-circumpolar. Let me explain what's going on here. If you're in the northern hemisphere like us, you may not realize this, but there's a part of the celestial sphere which we never get to see. And those are stars which hover around the south celestial pole, like you see in the yellow ring. And there's some really cool stuff down there that I've never seen that I wish I could. Like, for instance, in the southern hemisphere, the large and small Magellanic Clouds are little galaxies, and you can actually see them with your naked eye. They're orbiting the Milky Way. They're quite beautiful. Check this out. I wish I could observe in Argentina so I could see the large and small Magellanic Clouds. And no kidding, like, you can just like look up on the sky and you can see these things, these little irregular galaxies floating there. Wouldn't that be cool? As long as we're in Rhode Island, we can't see these things because they're below the rings that rise above our southern horizon. So to go back to, let's keep those two lines up there. So can anyone tell me what range of declinations never rise above the southern horizon?
Would it be negative 48 degrees to 0?
0 is the celestial equator. This is negative 48. I'll give you that. The celestial equator is 48 degrees above our southern horizon. So this is the declination of your southern horizon is minus 48 degrees. So you got the maximum, but down here is
Maybe like negative 22.
no
Negative 90.
negative 90 because it's 90 degrees from the celestial equator. It's the opposite of the circumpolar stars. That homework problem is tough, but a very good exercise for you guys. The rest should go a little bit smoother, a little bit faster. Vincent, I guess I'll have you read next because I had Fred and Caitlin do one.
Sure.
I'm going to erase. Hold on, David says 1 sec. David, I want those thumbs up when you're done. All right, cool. Vincent, when you're ready, chapter S143.
Okay, number 43. The title is Local Path of the Sun. Describe the path of the sun through your local sky for each of the following days. Part A, the March and September equinoxes.
You guys know how to do this?
So it would rise at 0 degrees east, correct?
Yep. And then,
It would reach 48 degrees altitude with an azimuth of 180 degrees south.
we're just going to use directions for this problem, just to keep it simple.
Okay, and it would set 0 degrees in the west.
Excellent. Which I will remind you is same as celestial equator. We already did this in class today, so I expected you guys to be quicker at this. Okay. Part B.
Part B, the June solstice.
Okay. Here's the picture from today. I'm going to repurpose this. I'm going to call it the summer solstice.
So your rise would be 0 degrees and north of east.
Yep.
Your reach would be 71.5 degrees and 180 degrees, or south, I believe. No,
Yep, just south.
yeah, south. And then your set would be 0 degrees and then north of west.
Yep. And we went over this in our lecture today. Right. Part C.
Part C, the December solstice.
All right, this one we didn't do today, but I bet we can get it pretty quick. Well, this will be a test to see if you're understanding or not. Here's the rise, here's the reach, and here's the set.
So your rise would be 0 and then south of east.
Good.
Your reach would be you would minus 48 from 23.5,
Or yes.
which would be 24.5 degrees,
Nice.
and then it would be 180 or west. No, south. Bad. It'd
The
be
sun
south.
gets highest in the sky in the south. Yep.
Yeah. And then your set would be 0 degrees and then south of west.
Awesome. I think this is useful stuff to know about. You're going to live on planet Earth for your whole life. The sun is kind of important. Maybe you should know how it moves across your sky. Not a terrible thing to know about. Lastly, part D.
Part D, today.
Now, we already kind of did this one if you think about it. Today is what is it, 28?
27th.
Sorry. The declination of the sun is negative 18 degrees. And I showed you how we use that, right? So what's the answer?
So would your rise be 0
Yep.
and then 0 and hold on. Would it be east?
Nope. It only rises east on the celestial equator.
Oh, so okay, so be south of east.
Yep. It would be some different angle south of east. We won't calculate that. That's a little tough.
Yeah. And then you would take 48 minus 18. So your reach would be 30 degrees and south.
Yep.
And then your set would be 0 and then south of west.
Good. And I referred to that earlier when I told, we actually kind of did this earlier. Because 48 degrees minus 18 degrees is 30 degrees. That's how we get that. Cool. Impressed. Very impressed. Last two problems are a breeze. Okay, chapter 3, number 53. Hey, these are going to be about Kepler's laws. I noticed David was jamming on his bass during our little tea break there. Kepler himself was a musician, Johannes Kepler. And one of the things that he did with his orbital period laws when he came up with p squared equals a cubed, David, is he wanted to use the periods of the planets to discover the natural harmonic vibrations of the planetary system. And he was trying to compose the song of the universe. So in Kepler's, he published his laws in Harmonices Mundi, or something like that, on the harmony of the worlds. And what's cool, David, is halfway through the book, after he develops his p squared equals a cubed, the book suddenly breaks into song and musical notation, and he starts using the periods of the planets to be their fundamental frequencies, their fundamental pitch, and he starts trying to compose the music of the planets. Every now and then, a musician such as yourself will actually go about and try to recreate them. It sounds like noise rock, though. It just sounds like we're all these from the couple of times I've heard people try to do it, it sounds kind of crazy. Kepler was an astronomer and a mathematician, but also an astrologer and a crackpot mystic and, a wee-woo kind of guy. So these two problems are going to be about Kepler's laws, and they're pretty easy, but I'm going to march you through them. David, on that note, do you want to read us chapter 353 for us? I agree, Mikey.
Yes, I have to pull up the thing first. So new planet orbit, a newly discovered planet orbits a distant star with the same mass as the sun at an average distance of 112 million kilometers, or 112 times 10 to the 6th. Its orbital eccentricity is 0.3. Find the planet's orbital period and its nearest and farthest orbital distances from its star.
All right, so we have to find the period. Now, you know how in our own solar system, we call them perihelion and aphelion? The fancy terms for this when you go outside to another solar system is we call it periastron and aphastron. But they have the same formulas that I taught you about today. To get the period, we're going to use p squared. P squared is equal to a cubed. That takes the average distance and helps you turn it into a period. By the way, the reason why they said it's the same mass as the sun is because they wanted Kepler's third law to hold. The periastron is found by the same formulas from the end of our lecture today. A times 1 minus the eccentricity, and the aphastron, which I use the variable APH for, is A times 1 plus the eccentricity. So some of this stuff might seem a little confusing at first because I didn't really lecture sufficiently on it. But basically, I just want to make you jam stuff into these formulas, and then I want you to think about it afterwards when I lecture on Tuesday. Here's the first trick to this problem. They gave us the distance in kilometers, but that is the wrong units for Kepler's laws. In Kepler's laws, A must be measured in AU and P must be measured in years. And this is really important practical advice for you guys, because I'm telling you, this formula is going to be on the midterm exam and it's wicked important. And what happens is students always forget what the units of P and A are. So I'm kind of trying to make that the first thing that we think about. How can I take my distance in kilometers and make it into AUs, which the formula will want? Hey, David.
Yes.
Doesn't this sound like a job for a special technique that I taught you, like the first day of class or maybe the second day? What's that technique called again, David?
I have to look at my notes.
It should have a big box around it. Second lecture.
4 steps of dimensional analysis.
Booyah. I want you to help me convert the kilometers to AU, and I want you to just walk through those 4 steps. What's the first? So wait, let's write down what we're about to do. We are going to convert the A to astronomical units. That's the job that David has for me, okay? That's step 1 here. So David, what's step 1 of dimensional analysis?
So you write down the number to convert it with its units.
So what should I write down then?
Would it be 112 times 10 to the 6th?
112 times 10 to the 6th, what?
Kilometers.
That's why I say with its units, because you can't just write this down. You have to write down the kilometers as well, or the whole thing will fail. Step 2.
Multiply by a division bar.
Step 3.
Put units in first to cancel.
So what does that mean? I need units top and bottom here.
So you would put in, would you put 0.3 on the top?
Whoa. Did I tell you start jamming numbers in?
You would put your
No,
units.
the units, sorry.
Yeah, you haven't earned the right to touch a number. Oh, wow. Did you see what's making that cool geometrical shape? There's some shadowy stuff going on here that I was enjoying. Anyways, no numbers until the units are in place, David. That's the secret. I need a unit top and I need a unit bottom.
So kilometers would go on the bottom.
Right? And
We're going to put AU on the top.
that's right, because I'm trying to convert to AU. And David, before you do anything else, let's remind ourselves why the kilometers went on the bottom, so that I could go and cancel out kilometers. What's step 4?
Put numbers in using conversion factors.
Now, David, you're going to have to hunt around looking for a conversion factor from kilometers to AU. It's got nothing to do with the 0.3.
It would be
Okay.
so it would be 1 AU divided by 150 times 10 to the 6th power kilometers.
Right. And let me show the class something. I have these lecture notes. Of course, I give you all these conversion factors, but never forget that if you can't find your conversion factors, you can sometimes find them quicker here just by grabbing the lecture notes. They're not great lecture notes, but they're kind of a review of the stuff that we talked about. And I usually put them in I put them in boxes in your notes, but you can see she's using this. I don't know what day it was, like the 3rd day or the 2nd day. 1 AU is 150 million kilometers, right? Okay. So sorry, which number goes where again, Caitlin?
So it would be 1 AU
So
divided
one goes
by,
on the top.
yep, one goes on the top, and then the bottom is 150 times 10 to the 6th power.
All right, use your EXP key and punch it up. Do this divided by that because it's on the bottom. You don't need to multiply by 1. That's a waste of time. Everyone punch.
You would keep 3 sig figs, correct?
Well, your conversion factor only has 2, so let's keep 2.
Okay.
Honestly, your conversion factor should never be screwing up your precision. Is it actually 150 to 3 sig figs? Why don't we find out? I think it's 149 point something.
Yeah, I might be wrong.
1 AU2. Yeah, it's 1 point. Actually, so if you round that, I guess it is 1.50. What is, who cares? Let's keep 2 sig figs anyways. It'll be cute. Come on, guys, this should take 50 fucking seconds. What's the answer? I don't want to die.
It'd be 7.5 times 10 to the 13th power AU. No. Must.
0.75.
Yeah. Hey, watch my moves. 112, EXP6. You got to use your EXP key. That's why you screwed up, Caitlin. Divided
No,
by
I know what I did wrong.
150. Yeah, you didn't use your EXP key. That's what you did wrong. 0.
No, I did times 10 to the 6th power.
Right. In other words, you didn't use your EXP key, which is what I said. But okay, 0.75. What are my units?
AU.
Okay. Now we can plug this into p squared equals a cubed. Okay. I need to erase. Can I do that? All right, here I go. Now I want you to watch how I do this. It's your first time around. If p squared is equal to a cubed, before I plug the values in, I'm going to get rid of the square. And I'm going to do that by taking the square root of both sides. The square root kills the square. So p is equal to the square root of a cubed. P then is equal to the square root of 0.75 AU squared. Oh, sorry, cubed. Yeah. Dum dum. Dum dum. All right. For these problems, let's take a peek at our Casio calculators here. Get out of here. Okay, if you guys can see this okay, the keys that we're going to want, there's your square key and there's your square root key. And your cube key is here. Your cube root key is there. You'll need both of these for Kepler's laws problems. But remember, anytime it's in orange, you have to hit shift first. So the way I would do this is I would do 0.75. And then I would cube it by hitting shift cube. You have to hit this button, the backspace key. And then I would hit shift square root. So I want to try that together, okay? 0.75, cube it by doing shift x cubed, and then shift square root. What do we get?
Would you round up to 0.65 or 0.65?
Yeah, 2 sig figs are good. What are the units?
AU?
No, p squared equals a cubed is a magical formula. It is magical because the answer automatically comes out in years. And the reason why I'm saying magic is because otherwise, instead of writing the formula p squared is equal to a cubed, I'd have to write p squared is equal to a cubed times years squared over AU cubed, and that would just be uglier. So rather than writing it ugly, what I will do instead is I will just say p squared is equal to a cubed, and magic happens to turn it into years. Understood? That's something you got to remember, or you have to write the formula in a hideous way. Okay, now that we have that, we also have to find the perihelion and aphelion distances. Perihelion is a times 1 minus the eccentricity. Always try to do the a in astronomical units because it's more elegant that way. 0.75 AU times 1 minus 0.3. And the aphelion is going to be a times 1 plus the eccentricity. 0.75 AU times 1 plus 0.3. When we plug these in, we will use our parenthesis keys. Parenthesis keys are located here and here. So watch me punch the first one and punch along with me. Watch this. 0.75 times open parenthesis 1 minus 0.3 close parenthesis, and that's going to do the parentheses, then you equals. What's my answer?
.52.
Round better. Your calculator shows 0.525.
So
You-
0.53.
Yeah, because you're rounding to 2 sig figs. What are the units? Please note that eccentricities are unitless. They're a percent squishiness. They have no units associated with it. So the units there are the units there. AU. That's how close the planet gets to its star. Okay, now you try. Do that one using the same technique. What do you get?
.98
Good. Units?
AU.
Killer. That's chapter 353. Almost done. Dennis? Hi.
Hi.
You down to read me the last one?
Sure.
Can I erase everyone?
No, I'm still writing.
All right, Dennis, let's give everyone a sec.
All right.
I'm getting a sip of iced tea. When I'm back, I want to do this.
I should have just told him I can't read.
Are we cool? I'm erasing. The next problem is exactly the same, different setup. Well, almost exactly the same. What's it say, Dennis? What's the title for 54?
All right. It says Halley orbit.
That's Halley's Comet, right?
Yeah, Halley's comet orbits the sun every 76 years and has an orbital eccentricity of 0.97.
The orbit of Halley's Comet is basically like a sausage. It goes way out past the orbit of Neptune and way interior to the orbit of the sun. Actually, let's keep that up. Yeah. The orbit of Halley's comet is so extreme. Wow. In 2024, it's basically at aphelion, right? It's as far from the sun as it can be. Well out near the orbit of Pluto. When I was a kid, because I'm, old, in the 80s, Halley's comet came by. I barely remember that, but I kind of remember it. And probably be dead by the time it comes around again. Okay, so what are we gonna do here? What's the problem?
All right, so the first one, A, is find its average distance from the sun. And then in parentheses, it says semi-major axis.
So I didn't really explain this, but the average distance or the semi-major axis, that's just A in P squared equals to A cubed.
Professor, was our class supposed to end at 2:55?
Yeah, well, look at it this way. Our lab goes 1 to 3. I'm doing your homework and I'm a little behind by about 5 or 10 minutes because I had some internet issues. So you can sit here and watch me do my homework for you, or you can try to do it yourself. I'll leave it up to you. If you need to log off, that's your business. I am just doing it as quickly as I can. This problem is going to take about 2 seconds to do. So why don't we just muscle through it? Sound like a plan?
I got a doctor's appointment, sir. I gotta go. I'll check out the video.
Yeah, just scroll to almost the end. It's only like another 5 minutes, okay? And Fred, do your doctors. Understood. We just got to get these problems done. That's all. Okay. P squared is equal to A cubed. That means A cubed is also equal to P squared. And I'm going to get rid of the cube with a cube root. Remember, guys, these office hours where I do your homework, I am not obligated to do this. I'm doing this out of the goodness of my heart. I'm not paid for this. This is pro bono work. I think it makes all of our lives better. You be the judge. Now, the units are already good because the period needs to be in years. So this is the cube root of 76 years squared. This is how we're going to punch that in. 76. First, we hit our square key, bada boop. Now we're going to activate the cube root. Shift, and cube root is the plus minus key. How many sig figs should I keep? Oh, sorry, wasn't it 76.0 years?
Yes.
So we can keep 3 sig figs. So what do we want to round it to?
$18.0.
Okay, that's not how this works. If you keep 3 sig figs, you keep 17.9. Now, if that number was 5, you could make it 18.0, but it's 4, so you leave it 17.9. To say 18.0 would be to lie. What are the units?
Years.
Remember, it's a magic formula. Right? Try again. AU. That was part A. Part B.
Right. Part B says find its, I don't know how to pronounce that.
Perihelion.
Perihelion, whatever, and aphelion distances.
Good. Same formulas from last problem. The perihelion is 17.9 AU times 1 minus 0.97. Aphelion is 17.9 AU times 1 plus 0.97. You guys should know how to do that. Punch them up for me.
0.54
Units?
AU.
The aphelion?
I feel like I'm wrong, but I ended up getting 35.3.
Let's just round it to 35. You can only keep 2 sig figs.
Oh,
because
that's right.
electricity.
Okay.
You're not wrong, you're right. Remember, it goes outside the orbit of Neptune. Neptune is 30 AU, Pluto is 40 AU. So that's just what we saw. All right. That was a pretty tough homework. In general, they won't all take quite so long, but today was confounded by several problems, one of which was I had some serious internet issues right up until 11:30 or 11:35. So I apologize, but I'm doing the best I can. Also, remember, when I was a student, you know who did these problems? Me, at midnight while drinking bulletproof coffee in the library. And the professor didn't help me do them. Okay. I think we're better off doing them together because you get better looking answers and you learn how to do it right. But homeworks take time. There's no two ways around that. That's part of the shittiness of class. However, now you're done and you don't have to think about astronomy until next Tuesday at 11:30. Please turn these homeworks in as soon as possible. I will get to the grading of lab 1. Thank you, Mikey. I'm glad to hear that. And you stay safe too, buddy. Get these homeworks and labs turned into me. I will at least grade lab 1 and homework 1 today. And maybe I'll do lab 2 and homework 2 if there's time. But I also have to do verification of enrollment. So if someone has not turned in any assignment, you're gonna get in trouble because you're gonna get dropped from the class. So please make sure you have at least something turned in. And good luck. See you guys Tuesday at 11:30, okay?
Bye, thank you.
Bye.
Have a good weekend.